Hello and welcome. Today we are going to talk about inclusion-exclusion. This is our final video on basic counting techniques. Our next series of videos will be about generating functions. Inclusion-exclusion is the technique that we employ to count the size of the union of overlapping sets. And this topic is our fourth and final basic counting technique. So even though it's been a while since we talked about the addition principle, the product principle, and the pigeonhole principle, today's principle of inclusion-exclusion belongs in their company. Let's start with an example. Recall that two positive integers are relatively prime when the only positive integer that divides both of them is 1. We want to count the number of integers between 1 and 1,000 that are relatively prime to 1,000. The prime factors of 1,000 are 2 and 5. So what we are really asking is which of these numbers are not divisible by 2 and not divisible by 5. Here is a Venn diagram of the situation. A2 is the subset of integers that are divisible by 2, and A5 is the subset of integers that are divisible by 5. And then we are interested in counting the number of elements in A that are not in A2 union A5. In other words, the set A2 corresponds to the bad event that k is divisible by 2, and A5 corresponds to the bad event that k is divisible by 5. So this is an example of good equals all minus bad, where the set of bad things is the union of two sets. Here is what a proof by inclusion-exclusion looks like. We start off overcounting by taking all the elements in the set A, including the bad ones. We then subtract off the sizes of the bad sets A2 and A5. However, there is a problem. The numbers that are divisible by both 2 and 5 are removed twice instead of once. So at this point, we have undercounted. We correct this by adding back the elements in A2 intersect A5, and we now have a proper count of the elements that are relatively prime to 1,000. So we include the set A, we then exclude the sets A2 and A5, and finally we include the set A2 intersect A5. Next, we must figure out the sizes of these sets, and this isn't too hard in this case. Half of the numbers in the set A are even, and so A2 has size 500. Every fifth number is divisible by 5, so the size of A5 is 200. And finally, a number is divisible by 2 and 5 if and only if it is divisible by 10, so A2 intersect A5 is 100. We plug these numbers into our inclusion-exclusion formula and find that there are 400 numbers between 1 and 1,000 that are not divisible by 2 and not divisible by 5. It's actually interesting to note that this value is also equal to 1,000 times 1 minus 1/2 times 1 minus 1/5. And we'll see that this pattern actually repeats in our next and more complicated example. So what about 3 sets? Let's look at how many times various subregions are counted by the formulas that you see. When we add the sizes of all 3 sets, elements that are in all of A, B, and C are counted 3 times, and elements that are in 2 out of the 3 sets are counted twice. And what about when we add the sizes of the pairwise intersections? Once again, elements in all 3 sets are counted 3 times, while elements that appear in just 2 of these sets are counted once. Finally, it's clear that counting the size of A intersect B intersect C counts those elements that are in all 3 exactly once. Our inclusion-exclusion formula for A union B union C works as follows. We include the elements of A, the elements of B, and the elements of C. This overcounts. Next, we exclude the pairwise intersections. This corrects the count for elements that appear in exactly 2 sets, but now the elements in all 3 are missing, so we have undercounted. Finally, we fix this by adding the elements that are contained in all 3 sets. Here is what an example looks like. We are interested in the integers between 1 and 1,200 that are not divisible by 2, 3, or 5. We create 3 bad subsets, elements divisible by 2, elements divisible by 3, and elements divisible by 5. These sets overlap, so we need to use inclusion-exclusion to get the right answer. Here are the details for calculating those set sizes. Ultimately, we find that 320 of the integers between 1 and 1,200 are relatively prime to 1,200. In other words, they are not divisible by 2 and not divisible by 3 and not divisible by 5. And once again, we can see that the algebraic answer actually has a really nice form. We multiply 1200 by 1 minus 1/2, and then by 1 minus 1/3, and then by 1 minus 1/5. We've actually proven two special cases of a result from number theory. The number of integers that are relatively prime to n has this exact same form. N times 1 over 1 minus p for every prime number p that divides n. The general proof is an application of inclusion-exclusion to the union of k sets. Let's write down the general inclusion-exclusion formula for the union of multiple sets. Here are the versions for the union of 2 sets and the union of 3 sets that we've seen before. The general formula gets a bit notation heavy. For each possible set size j, the inner sum includes all the possible intersections of j of the sets. The sign alternates between -1 and +1 depending on whether j is odd or even. As written, this formula is more useful as a conceptual roadmap of what to do, rather than an explicit set of directions of what to plug in. Here's the same general formula expressed using a more compact notation. We are summing over all non-empty subsets of the collection of indices, and we introduce the notation A sub s to mean the intersection of the AI sets where index I is in the set S. Note that this intersection gets included or excluded depending on whether the size of S is odd or even. I quite like this conceptual formula. It communicates the idea without getting lost in the nitty-gritty indexing details. It is also nice to have a formulation when the union of the A sub I is the set that we want to avoid. This is really useful in practice. Each set A sub I corresponds to one of the many bad events that we must avoid. In this case, the alternating sum is actually a little nicer. We just need to take the -1 to the size of the subset of the indices. But we must also note that we define A sub empty set to mean the original set A. After looking at the next example, I encourage you to come back to this slide and appreciate how this compact notation does a really great job at capturing the essence of inclusion-exclusion without getting lost in the details. We are now ready to do a complicated inclusion-exclusion example, and I want to give you fair warning. This example might be hard to follow the first time that you watch it, because I am going to talk about n different sets rather than talking about 3 or 4 sets. But this example is worth it. We will see many similar uses of inclusion-exclusion where we have an arbitrary number of sets. For example, this is how we will find the number of ways to create a surjective function. So I encourage you to rewatch this part of the video a few times. So let's begin. Suppose that we have n pairs of twins, so 2n people total, that must be seated around a circular table. How many ways can we do this? The answer is 2n factorial divided by 2n, which is equal to 2n minus 1 factorial, because after seating the people at the table, we must divide through by the 2n circular symmetries. Here comes the part where we need inclusion-exclusion. How many ways can we do this if no pair of twins is seated together? We cannot count this directly because the placement of the first set of twins impacts where we can place the next set of twins, and so on. So the number of cases that we would need to deal with skyrockets. And this is where inclusion-exclusion comes to the rescue. Let A be the set of all possible seedings, and let A sub I be the collection of seedings that are bad with respect to the ith set of twins. Namely, A sub I contains all the seedings where those two twins are sitting next to each other. The union of A1 through AN is precisely the set of all bad seedings. We have at least one set of twins that are sitting next to each other. And because good equals all minus bad, the collection of good seedings is just the complement of this union. So let's figure out the sizes of these various sets and intersections. We've already determined that the size of A is 2n minus 1 factorial. And remember that A contains all the ways to sit 2n people around a circular table. Next, let's find the size of A sub I. Since the ith pair of twins must sit together, we can treat them as one big person, which means that we are now seating 2n minus 1 people around a circular table. However, we must also multiply by 2, since these adjacent twins can swap places with one another. Therefore, the total number of ways that the ith twins can sit together is 2n minus 1 factorial divided by 2n minus 1 times 2, which gives us 2n minus 2 factorial times 2. So how about AI intersect AJ? This is like seating 2n minus 2 people around a circular table, and then we also allow the ith twins to switch chairs and the jth twins to switch chairs. So the total number of ways is 2n minus 2 factorial divided by 2n minus 2 times 2 squared, giving us a final answer of 2n minus 3 factorial times 2 squared. In general, when all the twins with the indices in the set S are sitting next to one another, the number of ways to do this is 2n minus the size of S minus 1 factorial times 2 to the size of S. If I take k to be the size of S, this formula becomes 2n minus k minus 1 factorial times 2 to the k. And next, we note that there are n choose k ways to choose a k set S. So the inclusion-exclusion formula becomes the sum of n choose k times minus 1 to the k times this term that we see, 2n minus k minus 1 factorial times 2 to the k. And what happened here is that all of our bad events were symmetric, meaning that the formula for a sub s only depends upon the size of the set S. And this symmetry leads to a simpler formula. The n choose k corresponds to the number of ways to choose the k indices, and then we use the same formula for the intersection of k sets. So this is our final answer, and note that it is not a closed formula because it includes one summation sign. It also includes one telltale feature that we are dealing with an inclusion-exclusion formula, which is that we are looking at an alternating sum, which corresponds to our alternate inclusion and exclusion of various intersections of sets. You'll be glad to know that this video's U-try problem is a little more concrete than the seeding twins problem we just looked at. Let's talk about the card game Set. It contains 81 cards. Each card shows a different combination of color, number, shape, and shading. And there are 3 choices for each feature, which is why we have 3 to the 4th, or 81 cards total. I want you to find an inclusion-exclusion formula for the number of ways to pick K cards so that you see both red and squiggle. These features can appear on a single card, or they could be split into 2 different cards that you hold. And my advice to you is to find 2 bad events. The first bad event is no red cards, and the second bad event is no squiggle cards. You need to set up the proper inclusion-exclusion formula to come up with your alternating sum answer. Good luck, and have fun.